Our next topic of discussion is factor of safety. So what is factor of safety? While designing a component, it is necessary to provide service sorry it is necessary to provide sufficient reserve strength in case of an accident. This is achieved by taking suitable factor of safety. The factor of safety is defined as factor of safety is equal to Fs is equal to failure stress upon allowable stress, or factor of safety is equal to failure load upon working load. Allowable stress is the value which is used in design to determine dimensions of component. For ductile material, the allowable stress sigma is obtained by following relationship. Sigma is equal to S by T upon factor of safety. Next is for brittle material, relationship is sigma is equal to SUT upon factor of safety. SYT and SUT are yield strength and ultimate tensile strength of material respectively. So in this factor of safety, first we have seen what is the definition of factor of safety and what is the need of factor of safety. So in this sufficient reserve strength in case of an accident we need to provide. That means suppose load acting is 10 kilonewton and on the component suddenly 12 kilonewton load is acting. So when maximum capacity of the component is 10 kilonewton and if we are applying 12 kilonewton, obviously it is going to fail. So from 10 kilonewton to 12 kilonewton increase in the load will get absorbed if we are designing that component based on the factor of safety. So factor of safety will take care of increase in the value of load and without breakage or without substantial change in the dimensions of the component. So factor of safety is failure stress upon allowable stress. Any component is there, in that component failure stress is higher than the allowable stress. So factor of safety should be greater than 1. Next, for ductile material, the design criteria is SYT, that is yield strength, and for brittle material design criteria is SUT, that is ultimate tensile strength. Next, we'll see now magnitude of factor of safety depends on first effect of failure. So what should be the magnitude of factor of safety? 1.5, 2, 3, what should be the value? That is decided by using the following parameters. First one is effect of failure. The effect of failure is not major. If it is very minor, then we can keep less factor of safety. But suppose effect of failure is hazardous, then we have to keep the factor of safety more. Next, type of load. Which type of load is acting on the component? Suppose type of load is static load, then less factor of safety we are keeping. If type of load is fluctuating load or increasing load, then we are going to increase the factor of safety. Degree of accuracy in force analysis. If we are able to calculate forces very accurately, then factor of safety will be kept less. If we are not able to find out forces and their direction accurately, then for safety purpose we have to keep the factor of safety more. Material of component. If the material of component is not costly, or material of the component is homogeneous, then factor of safety will be less. If the material of the component is non-homogeneous, factor of safety more. For example, if gray cast iron is there, which is obtained or the components are obtained by casting, in that case material is not homogeneous, so we are going to increase factor of safety. But if the material is made up of mild steel having homogeneous nature, we can keep less factor of safety. Reliability of the component. If the component is more reliable, if it is designed in the more reliable way, then factor of safety will be less. Cost of component. If the cost of component is not high, we can keep low factor of safety, like bushes and other things are there. of which cost is very less, so we are not going to keep high amount of factor of safety to it. But if the cost of the component is high, then we need to keep more factor of safety. Testing of machine element. If the testing of machine element is done accurately, properly, as per the norms, where we can keep less factor of safety. And if testing of machine element is not done properly, or if we are not able to do it properly due to non understanding of forces, then we can increase the factor of safety. Service condition. What is the service condition over there? Depends on that, factor of safety will either be more or less. Quality of manufacture. If the quality of manufacture is good, then we can keep less factor of safety. If quality of manufacture is of low grade, we may have to keep the high amount of factor of safety. Selection of magnitude of factor of safety means either factor of safety should be 1.5, 2, 2.5, 3, whatever value we are assigning. How we are selecting it? How to select the magnitude of factor of safety? First, the cast iron components. Ultimate tensile strength is considered to be the failure criteria for cast iron components. So that's why factor of safety is kept more, 3 to 5. For components made of ductile materials like steel, which are subjected to external static force, yield strength is considered to be criteria of failure, and magnitude of factor of safety is from 1.5 to 2. For components made of ductile materials and those subjected to external fluctuating forces, endurance limit is considered to be the criteria of failure. So factor of safety is in the range from 1.3 to 1.5. If cam, follower, gears, rolling contact bearing, such members are coming, which are coming by contact stresses, then theory of failure used is pitting failure, and for which factor of safety is from 1.8 to 2.5. Endurance limit, this topic pitting failure or endurance limit, we are going to study in the third unit, that is design against fluctuating load. Piston rod, power screw and studs are designed on the basis of buckling consideration. So factor of safety is from 3 to 6. Service factor. Again, one more important topic is service factor. And what is the service factor definition? The service factor is the ratio of rated horsepower or torque to the application's required horsepower or torque. Power is either provided by gearbox or by motor. That's why the definition is the service factor is the ratio of gearbox or motor rated horsepower to the application's requirement horsepower. In practice, the torque developed by the source of power varies during the cycle. Similarly, the torque required by the driven machine also varies. So torque varies both by the source as well as it is also vary with respect to the driven machine. When source we are considering like electric motor, then electricity variation may create some torque variation as per the cycle, and driven machine depends on loading and unloading condition, the fluctuation in the torque will get induced. The two sides are balanced by means of a flywheel. When your power required is less, flywheel will absorb the energy or power, and when overloading is there, flywheel will provide the power to the machine. In gear design, maximum force is the criteria. This is accounted by means of service factor. That means in gear design, if maximum force or maximum torque is generated, so that increase in the torque or maximum force, the service factor will account for it. So what is the definition of it? Definition is CS is equal to maximum torque upon rated torque, or MT max upon MT. MT is torque, so T max, tau max upon tau, or it is also called as starting torque upon rated torque for a motor. So for motor, we know that starting torque is more due to inertial effect. So CS, service factor, is starting torque upon rated torque. So here are some values of the service factor that I am showing. The first column is of working characteristic of driving machine, uniform, light shock and medium shock. And second column consists of working characteristic of a driven machine: uniform, moderate shock and heavy shock. So first one is for driving machine and second is for driven machine. So one can call it as a source, and that means one can call it as a source. This column is of source, power source, and this is for power absorbing device. This is also called as driving machine and this is called as driven machine. If driving machine is having uniform working characteristic and driven machine is also having uniform working characteristic, then factor of safety, then service factor is 1. Uniform driving machine and moderate shock driven machine 1.25. Uniform driving machine and heavy shock driven machine 1.75. Similarly for light shock driving machine and uniform driven machine 1.25. For moderate shock driven machine 1.5. For heavy shock driven machine 2. Similarly we can read the last row also. Now what are the examples of uniform and light shock medium? First one is for driving machine. So uniform, like electric motor, steam turbine, gas turbine. Light shock will be driving machines like multi-cylinder internal combustion engine. Medium shock is like single cylinder internal combustion engine. Then characteristic of operation for driven machine like generator, belt conveyor, platform conveyor. Uniform characteristics are seen. So what I meant to see from this, suppose I want to calculate from this chart, I want to calculate the service factor when driving machine is electric motor and driven machine is heavy elevator. So I can go for, so suppose I can highlight it, electric motor is our uniform characteristic operation for driving machine, and here is heavy elevator. For heavy elevator medium shock is there, so I will go for medium shock. We'll go for moderate means moderate shock, and uniform. So I can select 1.25 as my service factor, 1.25, and generally service factor ranges from 1.25 to 1.5. So these three table will help us to find out the correct service factor.